Thank you. Can I start, I guess? Hello, everyone. Welcome back to this conference. Thank you very much for having me. And like my presentation is entitled on the capacitated facility location problem with scarce resources. So let's go into that. So this is a joint work with Auricchio, Clough, and Zhang, which is here. And we are I am from the University of Padua, the other two are from the University of Bath, but we work together at the University of Bath. Then I changed my university. So here we are. And yeah, this is more or less the outline of what we're going to talk. We're going to talk about what framework are we working in. And we're going to study this problem from a mechanism design viewpoint, which means that we are going to define some mechanism and require some properties on them and do some worst case analysis, of course, and study some other properties more empirically rather than formally. So in this paper, we are considering, again, as the title suggests, the M-capacitated facility location problem from a mechanized design perspective. And we are considering the framework introduced initially by Aziz et al., in which they consider the case in which the facilities cannot accommodate all the agents. So, for example, you have 100 agents and only 70 of them can be accommodated. And you have to select the position of the facilities with their capacity and place them like along a line, because we're studying the case in which everybody is placed on a line, in such a way that you help them, and we will see in which sense you want to find the best possible location for that. But the premises are that not everybody is going to get a location, and we need to find a way to solve this problem. So we are not enforcing agents to facilities. Like this is another framework in which you open up the facilities and then decide which agents goes where. We are letting the agents free to select where they want to go. So to decide which agents gets allocated by a facility or not, we model the selection using a first come, first served game, which means basically that the agent that comes first to a facility that is not saturated can get accommodated by the facility. So mathematically speaking, what you have is actually a set of position, which is a vector x whose entries are actually between 0 and 1. So x is an n-dimensional vector that describes where the agents are actually located. And then we have a n-dimensional vector that contains the different capacities of the facilities, so that you have k1, k2, k3, k4, km with integer numbers. And we have a vector y, y1, y2, ym, which basically contains the position of the facilities and where we are going to open them. So that y1 is actually the position at which the facility with capacity k1 is opened, and so on for all the other indexes, basically. In our framework, we are assuming that the number of agents is lower than the total capacity of the facilities, as we said before. So not every agent is going to get allocated to facilities and will not get the service. And as we said before, the way to decide whether an agent gets accommodated or not is that after you open up the position of the facilities and you select them, they compete in a first come, first served game. And how it works, yeah, basically every agent selects one of the facilities. So the set of strategies of every agent is actually a number between 1 and m, which identifies which facility they want to go to. And then so for every facility, so let's say K1, the K1 agents that are closer to the facilities and that they also selected 1 as their strategy gets allocated with the facilities. While the other one are not getting any, they're not getting there in time, roughly speaking. You can think of that as like, I don't know, a set of supermarkets are actually open at the same time and they don't have enough milk for everybody. So every agent selects which grocery shop they want to go to, and they run at the same speed to this position. And the first one that comes are the one actually closer, and that also selected the facility that allow them to get closer. So it's about being closer to the facility opened, but also be one of the agents that wants to go there and that have a chance to get accommodated by the facility. And this is what is basically described in point 2. And finally, once like the agents have selected their facilities, the utility is defined as 1 minus the distance between their position and the facility that they get allocated to, otherwise it's 0. So we are considering this framework in which we have utilities. Like maybe other people know that in facility location problem, you are more likely to minimize the cost rather than maximizing the utilities. But this is the framework as was introduced by Aziz, and it does make sense because there is no standard way of defining what the cost of an agent that doesn't get allocated by any facility actually is. So we go for the utilities because if it doesn't get accommodated, your utility is zero. Otherwise, it's this formula, which is consistent with the case of the costs. So here, I also need to stress another point, which is basically one of the main contributions of the paper. So in this case, we are considering problems where we have more than one facility. And the paper we draw inspiration to start this research actually consider the case in which you have one facility only. And this is like this problem, this game becomes trivial when you have just one facility because everybody is going to go to the same shop because there is just one in town. In this case, actually, it's a little bit tricky. And now we show why. So first result, which is important, is that every time you open up some position of the facilities and for every position of the agents, the first come, first served game admits at least one pure Nash equilibrium, which is the starting point of our discussion. But this Nash equilibrium, this pure Nash equilibrium, does not need to be unique, unfortunately. And here we can see why. So for example, we are opening two facilities, like they are the green squares, and the red lines are basically the strategies of the agents that get accommodated. So in this case, you see that agent X3, which is the one in the middle, is equidistant from both the facilities. So depending on where it goes, agent X1 or agent X5 gets accommodated because it does not depend only on who you are closer to, but also what the other agents do. So this is important because you can see that like same position, same instance, but different equilibria, and more importantly, different utilities for different agents. So in this case, the agent X1 has a non-null utility, while in this case, the utility of the agent X1 is equal to 0. And the same goes for X5. And as I said before, we are studying a case in which we want to define truthful mechanism, which roughly speaking means that we don't want agents to be incentivized to lie to us, which means if you tell us the truth, like your real position in this case, you are going to be better off than telling us a lie. But in this case, it doesn't really apply because this guy does not get accommodated or not depending on whether he's telling the truth or not, but rather depends on what the agent X3 is actually playing in the first come, first served game. So in order to do that, we need to solve two problems. So first of all, we don't have a real like definition of what a truthful mechanism is. And the second one is that the utility of the agent and also the social welfare, which is the sum of all the utilities, is not well defined. So you cannot really study what are the performances of the mechanism because you want to define a mechanism and you want it to be as close as possible to the optimal outcome. But in this case, there is no true definition of what the optimal outcome is or what the social welfare of the mechanism actually is, because it depends on the strategies of the agent, and we cannot control them in this case. And again, notice that this issue only arises when you have more than one facility, because if you have just one, again, everybody's going to play the same strategy. You can predict that, and it's very much easier. So to overcome these issues, we actually introduced two new notations, two new concepts, which is absolutely truthfulness, which is, as the name suggests, a stronger version of truthfulness, in which we require that the agent is better off regardless of what the other agents are actually playing. So in this case, you have that your maximum utility, which is your best response, like this is the strategy of the agent Xi. And if he says this, if he reports correctly his true position to the mechanism, which means that here you have X and here is X, if he selects the best strategy, knowing the strategies of all the other agents, his maximal utility is larger than the maximal utility that he will get by reporting another position, in which case you have X prime, and he still plays a different strategy that is maximizing his utility. So again, like you tell the truth, and then you play your best strategy and you're better off, roughly speaking. So there is an extra step to this definition. And we say that an absolutely truthful mechanism is also equilibrium stable if for every Nash equilibrium of the first come, first served game, you have that the social welfare, which is the sum of all the utilities of all the agents, is the same regardless of the Nash equilibrium. So starting from two building blocks, we are able to extend all the framework and find some interesting result in this direction. So again, like those are some the definition. Again, when you have like an equilibrium stable and absolutely truthful mechanism, you can define univocally what the social welfare of the mechanism actually is. And you can define the optimal social welfare as the maximum social welfare attainable on the maximal on the best Nash equilibrium induced by Y. So in this case, we use this like sort of sleight of hand to solve the controversy on which Nash equilibrium we should consider, but this is in line with the price of finality theory and stuff like that. So don't pay much attention to that, that's fine. And finally, once we define what is the social welfare of the mechanism and what is the optimal social welfare, we can of course define what is the approximation ratio of the mechanism, which is the maximum ratio between what you can obtain using the optimal solution and what is the maximum rate between what you can obtain using the optimal solution and whatever the social welfare of the mechanism actually is. So this is a way to quantify what the error induced by your mechanism is. And the interesting part of mechanism design, as like people that have ever played with that knows, is to find a mechanism that is truthful, possesses a lot of like properties good for the social problem, and also achieves a low approximation ratio, which is as close as possible to 1, of course. And in this framework, we consider a mechanism that is well known, which is called a percentile mechanism. And roughly speaking, what you do is actually just taking some set of values between 0 and 1. So for example, 0.5, 0.6, 0.7. And then you compute this value, ij, and you place one of the facilities at the position of the ej agent from the left. So for example, if you select the percentile mechanism induced by 0 and 1, you're placing one facility at the leftmost agent and the one facility at the rightmost agent. And like basically the vector V is telling you the percentage of agent on the left and on the right of the agent at which you are placing the facility. And those mechanisms are well known in facility location because they are truthful, because like if you are the agent at which I am placing the facility, you have no incentive into lying to me because otherwise you will increase your cost. And if you're not, the only way you can really move the position is actually by reporting something on the left or on the right of the agent. But in doing so, if you think about that, you are moving your facility like further from you. So you have no benefit and no incentive to do that. And this is true also for this framework. So every percentile mechanism is actually absolutely truthful. So we are good. This is a very nice property to have for this problem. Unfortunately, this is not true, and this is the case m equal to 2. This is no longer true for equilibrium stability. So if you want the percentile mechanism to be equilibrium stable, you need to enforce this condition over the percentile vector, which is basically the vector that induces the mechanism. And this means basically that between the two positions of the facilities, you need to have enough agents so that you don't get this scenario that we saw before. So in this case, we have that the two facilities can accommodate two agents, but you see that in between them, there is just one agent. If there was one more, we wouldn't have like this situation. And also this example is particularly interesting because this outcome in which we place two facilities as two agents is actually an outcome of a percentile mechanism. So you can see from this instance that not every percentile mechanism were thought to be the same in this framework. Going back to this characterization, so we are able to select which percentile mechanism are actually suitable for our problem or not, and that's good. And after we identify them, we are also able to characterize what is the approximation ratio of every percentile mechanism that is actually equilibrium stable. And like those are some formulas that you can check, but the important thing is that even if you have two facilities, you see that this is something bounded, and people that works from the field of mechanism design, they know that usually when you have two or more facilities and you are considering the cost, the approximation ratio is equal to n minus 2 at best when you have two facilities, and is equal to plus infinity otherwise. So here we can see that by changing the framework, you can improve on that result. And this is even more, the comparison is even more interesting when you move to the case in which, oh, actually, no, there is one slide before that. And in this case, actually, when you characterize what is the approximation ratio of every percentile mechanism, of course, you can find out which is which percentile mechanism is the best, depending on the capacities of the two facilities that you want to locate. So we characterize all the approximation ratio for all the possible percentile mechanism and characterize which one are the best. And then, this is for the case m equal to 2, we moved on and did that also for the case in which m is larger than 2. For the sake of convenience, we just considered the case in which every facility has the same capacity, which is k. So we extended the first theorem in which we show that in this case, instead of one inequality, you have a system of inequalities that you need to satisfy in order to make the mechanism equilibrium stable. And after that, you can characterize what is the approximation ratio. And again, you can characterize what is the best percentile mechanism. And again, people coming from this field and that consider the cost rather than utility will know that whenever m is larger than 2, your approximation ratio is plus infinity and you cannot do best. But in this case, in some cases, you have that your approximation ratio is 1 plus something that goes to 0 as a function of m. And it does make sense because it means that you have enough facilities, enough facilities to cover up basically all the intervals. And in this case, you have utilities, so you cannot have anything that goes to 0 and have problems. But that it's good to see that you can bound what is the error in this case from something that depends only on the number of facilities. And then to close up, we had some experiment in which we are assuming that agents are sampled from a distribution. So up to now, we just consider the worst case analysis, which means worst possible input for the mechanism, what it is, the ratio, what are we losing. In this case, we are considering something on average. So it means that the agents come from a probability distribution and we want to see whether we are able to do better than that in this case. And what we want to assess with our experiment is basically what happens when you consider a percentile mechanism that is not optimal. So we are comparing the optimal that we found according to the worst case analysis with another percentile. And then we want to consider what happens when the agents are actually not identically distributed. So the first test will be about identically distributed agents. In the other case, we are considering agents that are independent but sampled from different distributions. And here, this is like the case in which you have an ID distribution, and you can see that the red one should be the approximation ratio of the best percentile mechanism, and the blue one will be the percentile mechanism that plays the facility at the leftmost and rightmost agent. And you can see that there is like a very large difference. Like the best one actually is stable, the other one seems to keep increasing as we go. And noticeably, like the approximation ratio in expectation is close to 1. So we are good to see that. And also, this is the case in which you have two facilities. So it's the one in which you have the worst approximation ratio if you go back to the previous slide. So we consider just this case. And here is when you have like different population and different concentration of agents with different, like, again, distribution. And in this case, we just consider the best percentile mechanism. And you can see that the approximation ratio is at most 0.01 or something very small. So it means that there is also room to improve our results when you assume that the agents are distributed according to a facility, according to a probability distribution. So another interesting step moving forward would be to characterize which is the best percentile mechanism that is absolutely truthful and equilibrium stable according to a specific probability distribution. And yeah, so to conclude, to wrap up, what we did is basically taking the paper from as is and extend all the results to the case in which you have more than one facility, which is significantly harder and requires some definition and some new concept. We characterize under which condition the percentile mechanism are viable for this framework. Again, like they have these properties and it's good to know that you can adapt them to suit this case. And we validated our results with several numerical experiments. And I guess that's all. Yeah, those are some references. So when I say that, oh, not this, okay, too much. Okay. So when I say that I extended this framework, we did that starting from this paper here. And the other one is about mechanism design and what are the percentile mechanisms. And I guess that's so. Yeah. Thank you very much for your attention.
on time like a Swiss watch.
Yep.
We have time for some questions, online or offline. So how does this whole picture change if you're not in a unit interval, but in richer metric spaces, higher dimensions?
So we are considering what happens in higher dimension, and the situation is much more dire. So we are extending this paper to send it to a journal, and we are doing that. So when you go, for example, to a square bidimensional, the set of truthful and equilibrium stable mechanisms is much narrower. So you lose all this characterization because basically nothing goes well. And this is due to the fact that the set of points that are equidistant between the two facilities, if you're considering just two facilities, is no longer just one point, but it's something that stretches, and you cannot bound that. Like in this case, we have two facilities, and whatever is in the middle can go both directions. But in this case, if you consider orders and you have higher dimension, these can get through the fact that you are considering an ordering on the coordinates to place the facility. So it's much more complicated, and there are very few mechanisms that works in this case, but we are working on that.
UAI next year.
Okay, UAI next year, yeah.
Other questions? Anything online? No.
Thank you very much.
Thank you very much. Next talk is Inference and Probabilistic Answer Set Programs with Imprecise Probabilities via Optimization by Damiano, Azzolini, and Fabrizio Riguzzi.
Yes.
Hope I said this right.
Yeah, right. So, hi, everyone. I am Damiano Azzolini from the University of Ferrara. And this 20-minute talk, I will present our article, which is titled Inference in Probabilistic Answer Set Programs with Imprecise Probability via Optimization. So, let's start from our contribution, right? So we cast inference in probabilistic answer set program with Cradle probabilistic facts and Cradle annotated disjunction as a constrained non-linear optimization, right? So there are a lot of terms involved, like such as answer set programs, probabilistic answer set programs, and so on. So let's try to analyze each of these terms in turn. So let's start from answer set program, right? We consider probabilistic answer set program, but just stick for now with answer set program. So an answer set program, and especially answer set programming, is a formalism, the powerful formalism to encode combinatorial probe. In this box, you can see an example of an answer set program. In the first 3 lines, you have facts, which represents what is known to be true. So we know that in this domain, A is true, B is true, and C is true as well. Then in the last 2 lines, you have rules. The first rule says, okay, if both A and B are true, then also Q is true. And the last line says, okay, if C is true, then either P or NP, the semicolon stands for disjunction, is true. Given this program, we can compute its answer set, meaning we can compute the solution that this program describes. And we get 2 solutions, which are actually called answer set or stable models. In the first solution, we have A, B, C, since they are known to be true. Then we have Q and P. And in another one, we have A, B, C, Q, and NP. So 2 possible solutions. Okay, now, but what happens if A, B, C are no more certain, but are uncertain? So what happens if we associate a probability value to A, B, and C? So another example, now you have inserted 2 probabilistic facts. We say that irrigation is on with a probability 0.2, 20%. And we say that rain is true with probability 0.3. Then we have still 2 rules. The structure of the rule is the same as before. Okay, if rain is true, then we are sure that the grass will be wet. And then if the irrigation on, either the grass may be wet or dry. Now we may be interested in computing the probability of a query. For example, what is the probability of wet grass in this scenario? And the whole pipeline is as follows. So we need to consider all the possible combination of truth values of probabilistic facts. We have 2 possible probabilistic facts. Each one can be true or false. So we have 2 to the power of 2 possible combination of truth values and tensor code words. in each word, we do not have uncertainty, right? Since we have fixed the truth values of the facts. And also we consider all the facts independent. For instance, when both irrigation on and rain are false, absent, this word has a probability of 1 minus 0.2, since irrigation on is false, times 1 minus 0.3, 0.7, since rain is false as well. We repeat this process for each of these 4 possible words, and we get the probabilities of each word. Now, how can we move from this probability to a probability of a query? Let's see. Consider the word where only irrigation on is true. So irrigation on is true, rain is false, so this rule is false as well. We are left with only this rule, wet grass or dry grass, if irrigation is on. This is a deterministic answer set program. There's no uncertainty, so we can compute its answer set, its solution. We have 2 solutions, one where irrigation on is present and also wet grass is present, and another one where still irrigation on is present, but this time dry grass is present, right? So we need to repeat this process for each possible word. Now, a word is associated with a probability, and the probability of the word is given by the product of the probabilities of the probabilistic facts, right? And the question is, now, how can we distribute the probability of this word on these 2 solutions? The answer is, in our framework, we do not distribute them. So we have a probability range for a query. Or, said otherwise, the query is described by a probability range rather than a sharp probability value. And a word contributes to both the lower and the upper probability of a query if the query is present in every answer set, every solution of the word. Otherwise, a word contributes only to the upper bound if the query is present in at least 1 answer set. So to make it even more clear, consider again this program I have just shown. So irrigation is true, rain is false. We have 2 answer sets, one with wet grass and one with dry grass. Suppose we are interested in the probability of wet grass. In this word, wet grass is true in only one of the 2 possible solutions. So in only some of the possible solutions. So we have a contribution to the probability value of 0.2, since irrigation on is true, times 1 minus 0.3, since rain is false. So we have a contribution of 0.14 only to the upper bound, since the query is present in only one of the 2 solutions. We repeat this process for all the possible words, and we get that the probability of wet grass is between 0.3 and 0.44. Now, let's get a little bit philosophical. So what happens if we are uncertain about uncertainty? Meaning, okay, let's extend the same example. Now, irrigation on is no more associated with a sharp probability value, but rather with a probability range. So we say that irrigation on is true with a probability between 0.2, 0.3, and 0.4. Similarly, for rain is true with a probability between 0.4 and 0.9. The remaining part of the program is the same. How can we compute now the probability of wet grass? Our contribution here, so starts here, is the following. So in the first step, let's ignore for a second the probability range. So we replace the probability range of each of these facts, which are called cradle facts, with a symbolic variable. For example, we replace the range 0.3, 0.4 with a variable we call PI, probability of irrigation, or whatever it is. And then we place the other range, 0.4, 0.9, with another variable that's called PR. Now, this is a probabilistic answer set program, as the one I've just shown you, without range, but with variables instead of probability values as probabilities. So we can compute the probability of a query. Again, how? As before, we multiply the probabilities of the probabilistic facts and we sum over the words. This time, we do not obtain a probability value, but rather we obtain an equation that describes the computation that must be carried on to compute the probability, right? If we replace PI and PR with a probability value, we get, in this case, LP, the lower probability of a query when the variable PI has value, I don't know, 0.2, and the variable PR has value, I don't know, 0.3, right? So this is a general formula, which is extracted from the program that describes the computation of the probability. We have two functions describing the probability of a query, since we have one for the lower probability and one for the upper. If you look close to this expression, okay, let's try to explode it. 1 minus pi times PR plus pi PR, we get PR minus pi PR plus pi PR. This can be simplified, and only PR is left, okay? This will be needed later, okay? Cool. How can we, starting from this equation and this program, going back to the original program, so compute the probability of the query when variable are associated with a range rather than a sharp probability value? We simply minimize the equation subject to some constraints. Let's go straight into an example. So this is our starting program. We have probability ranges. We replace probability ranges with symbolic variables, if you want. We extract an equation representing the lower and the upper probability. And then to compute the probability of the query, let's say WG, what grass, in the original program, is sufficient to minimize the equation we extracted from this other program, where the value of the variables must be in the range described by the original grid of facts. Okay, so by solving this optimization problem, we get the probability of wet grass in this initial problem, where the condition on may lie in the range 0.3, 0.4, and rain may lie in the range 0.4, 0. Okay, we had another syntactic construct to express uncertainty, which are trivial annotated disjunction, and as this form, so it's read as red is true with a probability between 0.1 and 0.3, or green is true with a probability which lies between 0.2 and 0.4, and blue is true with a probability which lies between 0.4 and 0.6. How can we perform inference in this kind of programs? Again, we did an additional step, and the additional step is the following. We can convert this kind of statement into a program by adding two new facts, still symbolic. We do not specify the probability of these facts as symbolic, and these are fresh facts that do not appear so well in the program. And then three rules that simulate this disjunction. So red is true if F1 is true, green is true if F1 is false and F2 is true, and blue is true if both F1 and F2 are false. And again, we repeat the same process as before. We obtain a program like this. We know to extract an equation, we extract the equation, and then we optimize. The only difference is that, okay, now the constants are a little bit more involved. This we need to account for this disjunction, right? Which are the constants for this simple program? The constants are, okay, P1 must lie in the range 0.1, 0.3, which is the original range that I want. Then P2, which stands for the green clause, okay? When not F1 will 1 minus P1 times P2 is true, this value must be in the range 0.2, 0.4. And then lastly, not F1, not F2, so 1 minus P1 times 1 minus P2 must be in the range 0.4, 0.6. Okay? So the process is the same, the constraints are a little bit more involved. Now, just give me a brief sketch on how we can extract an equation from a program. So a probabilistic answer set program can be converted into a negational normal form, an NNF, via a process which is called knowledge compilation. An NNF is a directed acyclic graph where internal nodes are associated with summation products. And so n node or nodes. And simply by traversing this NNF, okay, when we encounter an OR node, we sum the probability. When we encounter an n node, we multiply the probabilities. But now probabilities are described by a function, not by a probability value. So we obtain a symbolic equation from this kind of NNF. Even more formally, this can be cast as a second level algebraic model counting the program, just to give you the name of the task we are dealing with. So, briefly surveying the experiments, we use CPI as an optimization solver, which provides two constrained non-linear optimization problem with non-linear constants, Probabilistic and as well as QB. use SymPy to simplify the symbolic equation. If you remember from the example I show you, we can simplify the original equation. We are left with only one term. Okay, this is the main, say, idea why we decided to simplify the equation in order to allow the optimization solver to work properly. And we compare again to another existing tool, which is called the task, which only supports cradle facts. We created 4 synthetic data set with 2 different configurations, one strict, where the range of the facts is actually strict, and another configuration when the range of the facts is a little bit more loose, and also for data set with cradle disjunction. And here I summarize the main question we try to address with our experiments. The first one clearly is, okay, is our tool faster than the already existing tools? The answer is yes, often by a large amount. For example, there are instances where our tool requires 10 seconds, while DPASP 100,000 seconds, 1,300 seconds, 500 seconds. DPASP is based on enumeration. And then second question, does the probability range attached to these cradle facts influence the execution time? The answer is no, definitely no for DPASP, and slightly for our tool, but the difference are negligible. Third question, okay, which one between the 2 optimization algorithms provided by SymPy are, let's say, more suitable for our approach? And the answer is always Kubila, which is based on LA linear approximation. Instead of SLSPP is based on the least square minimization. And then an interesting one, okay, is the simplification of the equation so crucial? The answer is yes. It takes a non-negligible amount of time, where the total amount of time is given by, okay, conversion of this program into a compact form, we acknowledge compilation, extraction of an equation, simplification, and optimization. This is the total time. If we consider the time spent on simplification, this is up to the 50% of this time. Okay, so after the time is spent on the simplification, but at the same time, if we remove this simplification problem, and we compare the time required with simplification program against the time required without, you get that without the simplification problem, you get a time which is greater than, larger than up to 6 times with respect to the time required with simplification. To conclude, so we cast the inference in probabilistic answer set program with cradle probabilistic facts and cradle annotated disjunction as an optimization problem. The pipeline, we replace cradle facts annotated disjunction with probabilistic facts. We represent the problem in a compact form via a process which is known as knowledge compilation. Then we extract 2 symbolic equations, one for the lower and one for the upper probability. We simplify the equation and we call a nonlinear optimization solver that solves actually this optimization. We run multiple experiments on different configuration against an existing solver. Our approach has been proven effective. As a future worker, we would like to investigate faster solutions to simplify equations, since we deal only with summation of products. So quite simple equation, but rather the tool we use to simplify that equation require a non-negligible amount of time. We also consider other tasks such as maximum a posteriori inference with imprecise probability. And yeah, this is it. There's a QR code that directs you to the paper, and yeah, my references. Thank you.
We have plenty of time for some questions. Let's grill the speaker. Anything online? I'm myself quite far away from this. Okay. I'd be curious if you can sketch sort of a problem setup where this approach would struggle because the sort of search phase really explodes.
Yeah. It's so
get a sense for
if you want to have an idea of the scalability of this approach, currently, let's consider this kind of program. In this kind of program, you have 2 cradle facts. Okay. In general, you cannot scale up. The limit is up to 2022 possible cradle facts. So you can have at most 2022 possible structure of this type. Okay. So this is more or less the limit, since for each of these possible combinations, you have 2 to the 2022 possible combination to explore. And then for each of these possible combination, you need to compute the answer set. So it's quite a really expensive process. So yeah, these are currently the if you only have, instead of a probability range, a shared probability value, you can arrive up to 30. Okay, but yeah, there are still quite limited. You have a huge specificity, but yeah, you pay a cost, which is the inference cost.
And would there be an opportunity to do sort of additional pruning if, for example, I say, you know, there is an event here, but it is a priori a very rare event, you know, 10 to the -6 or whatever, and wherever you get squares or then don't even go there. Is there?
Yeah, I didn't talk about think about this, okay, but it could be an interesting idea. Moreover, sometimes the program can be, I would say, factorized, so you can consider different parts of the program on their own, and then in a certain way sum up the result or combine the results of different parts, and it will certainly help the inference process. But I didn't try it yet.
Okay.
Hello.
Hi.
Hi. Oh, thank you for the talk. It was very interesting. I have 3 questions, but maybe okay. One, it's quick, but since you are solving a nonlinear optimization problem, you are not guaranteed that the lower upper limit are exact.
Yeah.
So this one. And the second, so if I understand correctly, you use symbolic calculation to compute basically the objective function.
Yeah.
But so have you thought about, so are you using like gradients for the optimizers or not?
Yeah, we just use this optimizer, which is the other way. ShePy that provides these 2 algorithms. I am not sure whether they require the gradient.
Okay, so you are using basically the numeric.
Yeah,
because I mean, I think you probably could do it's using automatic differentiation.
Yeah, it could be an idea. Yeah.
And the third one, have you heard about sum of square programming?
Sorry?
Sum of square optimization.
I don't know. Yeah, I've heard the term. I never.
Basically, it's basically you solve a polynomial optimization problem but you have guarantee that what you solve is a lower bound of the original problem. So it's provided something maybe you could investigate because you have already the pipeline for the polynomial symbolic optimization. That is the difficult part there.
Yeah. Thank you. Of course, I will try it.
Thank you.
Thanks, Damiano. Very interesting. I have a question. Can you go back to the slide with the wet grass?
Sure.
The initial one.
This one or even before?
Well,
this?
Yes, it's okay.
Okay.
So here you are not specific. Suppose I want to specify probability range also to the rule, like wet grass to dry grass.
Yeah.
Right? Is it something you can use annotated disjunction to deal with it? Maybe like some preliminary transformation as they do in Broadrick, for instance, to turn probabilistic rules into, no?
Yeah. If you want to also specify a probability range for instance, you also want to attach a probability to wet grass, you can just simply put another critical probability factor in the body.
Yeah.
Like in Probabilistic. Okay.
And this is the same for the annotated disjunction.
Yes, it's the same. Yeah.
Okay, thanks.
Sure. And also, just to conclude, here I've simply used a propositional program, but you can also clearly first order program with variable and so on.
Hi, thank you for the talk. I just wonder if you know the bulk and pearl bounds or like principal stratifications in epidemiology, where people, the query is a polynomial functions of the kind of set in there, and they try to also use optimizations to solve that. I'm not familiar with answer set, so it just occurred to me that it's kind of similar. So just wonder if you know or can comment on that.
Yeah, I don't know the framework you mentioned, so I cannot be much of help. I'm sorry, but I don't know.
Thank you.
Maybe it's a naive question. Why can't you just instead assume you have some sort of distribution, right? Priors, what does your framework, what kind of problems would it solve that you can't just model by assuming uncertainty about random variables in terms of priors?
I mean, yeah, this is a good point. I would say here we only consider this kind of distribution, so only the Bernoulli distribution, okay, if you want here, and then setting on rates. But I didn't think about also using prior distribution. So I don't really have an answer to your question, right? So I'm sorry, but yeah, maybe it's not something I will think about.
Any other questions? Okay, let's thank the speaker again.
Thank you.
So this concludes the part of the session devoted to delivery with Italian pizzazz. And we now switch to a bit of French je ne sais quoi. Next talk is Generalized Expected Utility as a Universal Decision Rule, a Step Forward by Hélène Fargier and Pierre Pomeret-Coquot.
Yes, so thank you very much. No, so my name is Pierre Pomeret-Coquot, and I did work with Hélène Fargier. We met at the IRIT laboratory in Toulouse, France. So it's called Generalized Expected Utility as a Universal Decision Rule, a step forward, because we extend an existing result from 2004. So during the presentation, I will base all my example on this decision situation, in which we will consider an urn, which might contain some pink balls and some blue balls. So you will have to choose either Chi pink, Chi blue, and Chi O. Then I will draw a ball, and depending on the color of the ball, you may either win or lose or get a tie. So if you choose Chi pink here, you will win on pink balls and lose on blue balls. And if you choose Chi blue, of course, it's the converse. You will win on blue balls and lose on pink balls. If you choose Chi O, you will neither win or lose, but you will obtain ties. So such a decision situation is formally defined by three sets. We have the set omega of states, we have the set X of possible consequences, and then the set A of available acts. So an act formally is a function mapping state to consequences. As for Chi pink here, mapping pink to wins and blue to loss. So dealing with such a decision problem, what we want is to infer a preference relation on acts, which may be a total ranking, a partial ranking, even a circular relation or anything. And we have many ways to do so, because of many decision rules may apply to build this preference relation, depending on the kind of knowledge we have, depending on the kind of preferences we have, and of course, depending on the decision behavior we want to model. So consider the first example here. We suppose we know exactly the content of the urn, that there are exactly 3 balls which are pink and 3 other balls which are blue. So this knowledge is perfectly well captured by a probability measure, stating here as many chances for pink as for blue to obtain. And furthermore, we will consider this utility function in which we encode the fact that losses and wins compensates. So you may all know that one of the criterion able to deal with such a probabilistic setting is the expected utility. According to the expected utility, all 3 acts have an expected utility of 0, so all 3 acts shall be considered equivalent. Okay, so now consider the second example in which we have many less knowledge. We only know that the possible color are either pink or blue, but we don't know much. So that's what we call total ignorance, because in fact, every outcome is equally and totally possible. So here we cannot apply expected utility without further assumption, but we can apply other criterion, like for example, the wild criterion or maximin or robust criterion, which are meant to consider the worst case utility. So according to this criterion, Chi pink and Chi blue are worse ranked than Chi. So in 2003 and 2004, Chu and Alpern proposed an algebraic decision rule they call Generalized Expected Utility, or GEU, which is parameterized by a parameter E here, a tuple, setting the domain and the operators. So in fact, we don't have really the choice for the domain because they are constrained by the decision situation, but we may choose the two operator O times and O plus. And by doing so, we hope to recover existing decision rules so we can study them all at once. So this algebraic decision rule enables to recover the expected utility using sum and product as operator. And it also enables recovering the wall criterion using the minimum here for O plus. And we have many choices for the O time operator because total ignorance is a very, very particular kind of knowledge. But we can also consider the minimum for this operator. Now consider this third example in which we have a partially precise and partially imprecise knowledge. We know there are 6 balls in the urn. 2 are pink for sure. 2 other balls are blue for sure. And the 2 last balls may be either pink or blue. So this kind of knowledge is perfectly well captured by a belief function. Here stating the minimal belief for the event pink is 1/3. As for the minimal belief for the event blue, and of course, the belief of the event pink or blue is 1 because we're sure of obtaining one of those 2 colors. This may be understood as a lower probability for each event. But in belief function theory, one often consider a so-called mass function, which can be deduced from the belief function and from which we can recover the belief function. That is to say, those 2 functions are equivalent. And mass functions also make sense. Here we have 3 focal elements that are the elements with a non-zero mass. The first one states that there are exactly 1/3 of the ball which are pink for sure. The second that 1/3 of the ball are blue for sure. And the last that the last third of the ball are either pink or blue. So here we cannot apply expected utility without further assumption, but we can apply a generalization of expected utility, which is called the Choquet integral or Choquet expected utility. This decision rule has a simple expression of the mass function. And in order to be the most clear as I can, I unfold here the computation for the Choquet integral of chi-pink. So we will iterate over all focal elements. On the first one focal element, we're sure obtaining a utility of 1, hence this local computation. The same is for the second focal element blue. We're sure it leads to a utility of -1, hence this local computation. And for the last focal element, which has 2 states, it may lead to 2 possible degree of utility, +1 or -1. And the Choquet integral here consider the minimum. So according to this criterion, chi-pink and chi-blue are worthily ranked than chi-O. And here we reach the limitation of the GEU framework because the GEU framework is not able to capture the Choquet integral, neither those for the Sugeno integral or other fuzzy integral and their variation. And that's what motivates our work, is that this generic framework is not generic enough for for dealing with all significant cases. So we want to improve it and to enhance its expressiveness. In order to do so, as for true and helper, we rely on algebraic capacities, which are simply a monotonic set functions that yield the value on an abstract scale W. So this is the case of all imprecise measures we can consider in decision theory, as for the 3 measures we have considered in the previous examples. One of the properties we can have on algebraic capacity is called decomposability. And we said a capacity is decomposable with regard to an abstract operator box plus if one can recover the belief of any event from the belief on the states only, on singletons. So of course, you all know that probability measures are decomposable with regard to the addition. And for those who know possibility measures, they may also know that they are decomposable with regard to the maximum operator. But in general, belief functions are not decomposable. We cannot find any operator that enable this recovering of beliefs. And that's where the GEU framework fails, because GEU cannot cope with decision rules that rely on the non-decomposability of capacities. So in order to overpass this limitation, we propose to consider algebraic mass function with regard to an abstract operator. And so we can recover the belief on an event, not only by considering states, but by considering masses of all subsets of its events. And we will recover the 2 classical settings, the quantitative settings using addition, we have the probability, we have the belief function, and more generally, all the kind of imprecise probabilities. And with the operator maximum, we recover the qualitative settings as for total ignorance and possibility failure. We have distribution as a special case, where all focal elements are singletons. Focal elements are elements which have a non-zero mass. That is to say, all mass are only on states and never on set of several elements. But in general, for a given capacity and a given box plus operator, there may be 0, 1, or several mass functions. So we have shown that this mass function exists and is unique as soon as the box plus operator has an inverse operation. And in this case, we provide an algorithm in order to build it. We call algebraic Mobius inverse. Okay. So if we recall the belief function from example 3, we already seen that it has a plus-based mass function, which is a classical mass function with 3 focal elements, each having a mass of 1/3. And we can recover the belief of any event just by adding all masses of its subsets. But we can also look for other kind of mass function with regard to other operators. And this same belief function also admits a max-based mass function, here with mass of 1/3, 1/3, and 1. And we can recover the belief of any event by looking for the maximal mass in its subsets. Okay. So on top of that, we define this algebraic decision rule we call XEU, which is parameterized by a parameter E, setting the domain and the operators. Here we are 4 operators to choose in order to recover the decision rule we want. The first operator is box plus, the mass function operators, which tell how to encode the knowledge. And as we have seen, we will then iterate on focal elements, but focal elements may be set of several states, so it may lead to several possible utility values. And in order to deal with those several utility values, we propose to use a function f, which take all those utility values as inputs and yield a single utility value as output. His goal is to yield a representative utility value in order to summarize all those possible values. So this representative utility will be then combined with its corresponding mass with O time. It will yield a local score, and then all local scores are aggregating using O+. So of course, we can then compare acts by comparing the XEU scores. Inside the XEU framework, we can recover rules for decomposable capacities as the 2 rules I present in examples. The expected utility is recovered with a plus-based mass function and sum and product as operator. And the 1 criterion here expressed as a particular case of probabilistic pessimistic utility is recovered with using max-based mass function and the min and max operator. In this case, with decomposable capacities, all focal elements are singletons, are states. So the F function here is not really useful because in case it has a single input, it acts as an identity function. But we can also recover rule for non-decomposable capacities. As for example, the Choquet integral I already present. Here we see that we have a plus-based mass function, sum and product as operator. And here in red, it is our F function, which serves to summarize the several utility values when needed. So F is not useful for the 2 first focal elements because they are singletons, but for the last focal element, F serves to yield this representative value. Another rule Jaffray proposed for belief function, so is this one, in which for each focal element, we will consider a trade-off between the minimal possible probability and the maximal one, with some alpha parameters like local Hurwitz coefficients. So here, all these red parts become our F function, called here min-max. And as before, we can see it is not very useful for singleton, but it will serve to yield this representative value when several utility values are possible. My last example is a decision rule from the transferable belief model, in which one manage knowledge using belief function, but when a decision has to be made, one recover an average probability measure and then decide according to the expected utility. So by unfolding definition, one can recover this formulation for the decision rules expressed on the Belief function. And we can see here that our F function amounts to compute an average utility, a mean utility. And as before, F is not very useful for singleton, but serves to yield here a representative utility value. Okay. So what I want to emphasize with the three decision rules is that they deal with the same kind of knowledge and they manage part of precise knowledge the same way, which is the expectation way with sum and product. So it's quite natural to have the same box plus operator, which serve to encode the knowledge and save O time and O plus operator here. On the other side, they differ on the way to manage ignorance in case of several utility value are possible, and that's why they differ only on the F function. So what I want to say is that F serves to capture the decision-making behavior under ignorance. And we can see as particular case, when we are in case of total ignorance, everything is possible. So the only focal element in this case is omega, the whole set omega with mass of 1. So the XEU expression simplifies, and simplifies much because we can see that it only F function remains, and F serves to deal with behavior under ignorance. So here it is in this table, I summarize some of the existing decision rules. We can see in the top part of the table the expected utility and the three rules I said in the past examples, which all are typical quantitative settings with plus-based mass function, sum and product as operator, and they differ on the F function. And when knowledge is totally precise, F function is not very useful, so we can use here everything. It is not a minus, it is just to say every F function is possible. In the second part of the table, you have the decision rules for the qualitative settings, like for the Wald criterion and the probabilistic utility criterions, and the general Sugeno integral. They all rely on max-based mass function and min and max operators. And then we have also some exotic decision rules which relies on exotic domains, like for example, R circle, which is a domain made of pairs, each pair denoting for an order of magnitude of probability. So having such a decomposition with the operator, it becomes quite easy to understand which kind of behavior decision rule captures. And it also becomes easy to define new decision rule. Here, I make a proposition, which is a variation of the Sugeno integral. And I don't have to test it. I can affirm what behavior it encodes. It encodes a similar behavior, but which be a bit less severe dealing with uncertainty because the median here is not as drastic as the minimum. Finally, we focus on how expressive is our framework. We first ensure that it is at least as expressive as the previous GEU framework, and it is. And then we have shown this representation theorem stating that only a very weak condition is necessary for a decision rule to be capturable by the XEU framework. This condition we call restricted uniformity is satisfied by decision rule which consider equivalent any two acts leading to the same utility with the same beliefs. So it is a quite common property. Okay, so in order to conclude, I can recap that we propose to consider algebraic mass function and that we provide algorithm in order to build those algebraic mass function. And on top of that, we propose the XEU algebraic decision rules, which extend GEU to non-decomposable measure and to almost all meaningful decision rules. In particular, I emphasize the fact that the XEU differentiates with those operators the behavior under total ignorance, even partial, and the behavior under precise knowledge, and that it makes easy to understand what kind of behavior decision rule encodes, and it makes also easy to define new decision rules. As perspective, we aim to study how axiomatics can benefit such a framework, and in particular, we think about a set of axioms for ignorance management and another set of axioms for precise knowledge, decision and precise knowledge. In the same vein, we aim to see how we can make decision rule elicitation with method for ignorance and method for decision with precise knowledge. And finally, we aim to see how this framework may be tractable in practice, because mass functions are known to be often sparse, and hence enabling tractable algorithm in the classical case of clause-based mass function. And so we aim to see what kind of property we need on the abstract mass function in order to have such tractability. Okay, thank you for your attention.
Thank you very much. Questions?
Thank you. That was super interesting. I'm going to ask something a bit naive because I'm not very familiar. But I was wondering if could your F function encode something like alphabetical order, and is that sort of contradictory to belief theory in general? And like, is it a bad thing to have like no structure under what the F function could be, and how much structure exactly does it have? If that makes sense.
Please, can you please rephrase the question? Speaking a bit less, a bit more slowly, because I'm not very good in English. Yeah.
Yeah, sorry. I just imagined if one had total ignorance under blue and pink balls, and one picked blue balls because they were earlier in the alphabet, does your framework exclude that as a possible belief structure, or does it include it? And is that a good or a bad thing?
If I understand well, I think the framework is able to capture, because the framework does not rely on the structure of the knowledge or the structure of the preferences. For now, just how to say, just functional setting, mathematical setting, and that's what we like to see. It's how structure may enable or not tractability and computational approaches.
Okay, thanks.
Is that good? Your question, is that good answer?
Yeah. I just imagine maybe looking into the structure on F might be a future direction or something. I'm really unfamiliar with the field, so I'm probably saying rubbish.
Okay.
But, thanks.
Other questions?
Are you considering any data-driven approach based on this analysis for the future?
Yeah, we don't have made it already, but in fact, data-driven approach may come from the two last perspective I said. For of course for experiment, but for decision rule elicitation, we have interest in modeling the human behavior. So those methods amounts to collect data from the decision maker, and from those data to how to say it? To identify how knowledge and utility are mixed for these people.
Online. Any other questions? We have time. No? Thank the speaker again. And last but not least, Polynomial Semantics of Tractable Probabilistic Circuits by Oliver Broadrick, Honghua, Zhang, and Gui van den Broek.
Thank you very much. All right, so I'll be talking about tractable inference. And before I get into that, a quick advertisement. If you find my talk interesting, or maybe even if you don't find my talk interesting, there's a workshop tomorrow all about tractable models. So come check that out. All right, so this is joint work with Honghua and Guy, and let's get into it. So the basic problem in probabilistic modeling is to find useful representations of probability distributions. And in this work, I'm going to focus on multivariate distributions over binary random variables. So here's an example over two variables. This table is great. It can express any such distribution. But of course, it's also not so great because as the number of variables increases, this table will go exponentially in size. And so really, we want succinct representations. And so that's going to be captured by this notion of expressive efficiency. So for example, take transformers or diffusion models, VAEs. These are models which are very expressive without requiring exponential size, say, for a rich class of distributions. But then on another axis, you have tractability. And so maybe less expressive models like fully factorized models, HMMs, so on, which support exact and efficient inference for a richer class of inference tasks, but maybe aren't so expressive. And so we're going to be interested in for an inference task that you want to remain tractable, what's the most expressive efficient model that you can design for that class? The question mark's up there. What can we find? Okay, so to instantiate tractability in a meaningful way, we need to pick a query class. And in this work, we focus on the fundamental task of marginalization. So this involves computing likelihoods, marginal probabilities, the normalizing constant or partition function, conditional probabilities. So it's a very useful class, but also it's a hard problem in general. So just for the two variable distribution, if you want to know the probability that x1 is 1, you have to sum over the variable x2. So it could be either 0 or 1. You have to sum the probability of these two worlds. And that sum can be over exponentially many terms in general. So this is hard. But when you have special structure in the distribution, this becomes tractable. So our goal is to find maximally expressive efficient models that still support marginal inference in time polynomial in the model size. All right. So this isn't a new problem, of course. There's tons of existing approaches to this problem. So Bayesian networks, for example, support efficient marginalization when the tree width is small, determinantal point processes, some product networks, and the list goes on. A sort of nice perspective about all of these models is that they can be viewed either very directly or after some efficient compilation process as succinctly expressing some polynomial, where that polynomial encodes the underlying distribution in some way. So somehow these all seem the same. They're just representations of polynomials. Okay, but actually the polynomials come in different flavors, different semantics. And so the semantics of the polynomial tell you how it encodes the distribution. And we want to understand the relationship between these. Like I said, I want some really big class that still supports tractable inference. And here we sort of have a fractured state of affairs where there's 4 different ones, and I want to know how they relate. All right. So I said succinct representations of polynomials. Each one of these would have exponential size in general. But as a general representation language for representing them succinctly, we're going to use arithmetic circuits. So these are just computation graphs with sums and products, where and then the leaves are the indeterminates of the polynomial. Sums are labeled by edge weights, so they compute weighted sums of their children, and products compute products of their children. And so this circuit represents that polynomial there. And in general, a circuit representation is fully expressive, meaning that it can represent any polynomial. This isn't hard to see because you could just sort of enumerate all the monomials in there. Of course, that would be huge. In particular, they can also be expressive efficient. So you can get a very concise circuit representing an interesting polynomial. All right. So we have these 4 different semantics, and each of them has been studied on their own in their circuit representation as a tractable model. In fact, with marginalization algorithms being developed, tailored to each individual semantics. But as I said, we want to study how they relate to one another. And a little bit is known. So if you have a circuit representing this network polynomial, and don't worry, I'll define the semantics later. That's like the rest of the talk. If you have a circuit representing the network polynomial, you can efficiently, like in polynomial time, convert it to either the generating or the likelihood polynomial for the same distribution. But the remainder of the relationships were not known before this. And so one of the main contributions of our work is that all of these relationships actually hold. which may be surprising. Actually, when I started this, I was thinking that we might be proving separations and that certain distributions could be captured in one semantics, but not another. Okay, but it turns out, in any of these semantics, you can, in polynomial time, transform to any of the others. All right, so the remainder of the talk is going to go through at a high level each of the four, and then say how we can relate it back to the others efficiently. So let's start with the network polynomial. This goes back to Bayesian networks. This is like a common compilation target for Bayesian networks, hence the name. And it encodes the distribution in a very simple and well-structured way that makes marginal inference very easy. So the colors aren't so clear maybe, but like just look at the top entry, the purple world will be encoded by the monomial 0.1 x1 bar x2 bar. So the indeterminates here are like positive and negative literals for each variable. And then the x1 bar and x2 bar correspond to the fact that in the purple world, the values are 0 and 0. So you can just easily encode every world with the literals this way, and then stick as the coefficient of that monomial the probability of that world. Okay, so simple encoding. And now this is really easy to do inference with. So if you have some black box way of evaluating this polynomial, there we go. So if you want the probability that x1 is 1, we have to sum over the values of x2. Well, we can set the x1 and x1 bar according to its assignment. So set x1 to 1 and x1 bar to 0. And then just set both the positive and the negative literal for x2 both to 1. And then you sum both the worlds that you want to. So the rightmost two worlds in which x1 appears in its positive form and x2 appears in either form. So you get 0.7 as we want here. All right. And then just keep in mind that we're really studying circuit representations of these because the flat representation is huge. You want a succinct representation. So here's an example of an arithmetic circuit that represents the polynomial we just saw, the network polynomial for this distribution. And then why is this a tractable model? Well, as we saw, if you want to compute this query, set the leaves according to their inputs, and then just like do a feed forward pass, and the output 0.7 is what we want. All right, so that's network polynomials. Next, we'll look at likelihood polynomials, both sort of how they're defined and then also how we can relate them back. All right, so this is a really fun semantics because it's maybe not obvious whether you can do marginal inference if you have a circuit computing this polynomial. But at the same time, it's a very simple polynomial. So what is this? It's just the unique multilinear polynomial that as a function of its inputs computes the probability of the world. So just, you can check the 0, 0 world. You'll pick up just the constant term 0.1, which is the probability of that world. And so this, doesn't have all the special structure that the network polynomial had. We no longer have the extra negative indeterminates. But actually, it turns out, well, okay. Do we have marginal inference? So this actually wasn't known for this semantics. It was known for the others, but this was an open question for this semantics. And then we want to know its relation to the network polynomial. Okay, and then one direction is easy to see. So if you have a circuit computing a network polynomial, you can get to the likelihood semantics by replacing those negative literals with 1 minus xi. And it's not hard to check that by interpolation. This gives you what you want. Okay, but it's the other direction which is maybe not obvious. I'm going to give like a quick example of sort of intuition for how this can be achieved. So here's the same likelihood polynomial we just had. Our goal is to get to a network polynomial. Just focus on the blue highlighted monomial as an example. In the network polynomial, we have, a monomial corresponding to every world. And here the 0.2x1 will actually sort of be active or be summed anytime x1 is 1. So regardless of the value of x2. And so what we really want is 2 copies of that, one with an x2 literal and one with an x2 bar literal. Okay, so here's a kind of trick that allows us to do this without, sort of doing it by enumeration. You can replace all the xi's with this fraction, xi divided by xi plus xi bar, and then multiply out front by the product of all those gadgets. And then what we have when we distribute, well, for the blue term, the x1 gadgets cancel, but then the x2 gadget gets picked up. And so now if you distribute once more, you get exactly what we wanted, 0.2 x1, x2, and 0.2 x1, x2 bar. Okay, so this is the network polynomial. So that's, as an example, sort of at a higher level, if this triangle is our likelihood circuit, you can just form this expression. And already this gives you linear time marginal inference because it's, you can efficiently form this expression and then you can evaluate it and do marginal inference because this as a function is computing the network polynomial, even though we started with that less structured likelihood polynomial. Okay, but there's sort of one catch, which is that there are divisions at each of the leaves. So I had said just sums and products. These are the kinds of circuits that people actually implement. So it'd be nice if we could remove those divisions. And here we get to rely on a really cool result from Strawson in the 70s, which says that, okay, you can remove divisions in polynomial time. So if you have an arithmetic circuit computing a polynomial, but it does use divisions, so it has divisions in there, you can sort of propagate the divisions to a single division node at the root, using simple identities. And then you can use like a clever application of the geometric series identity to get rid of that single division. And so this is quite nice because in particular, you start with something which you know is a polynomial, except for at finitely many points, there are holes. And then what you get at the end is exactly the like clean original polynomial. So you get rid of the holes sort of magically. And this actually becomes important in a second. Okay, so the punchline for the likelihood polynomial is that you get to do this last single step where we remove the divisions and we just have a nice circuit computing network polynomial. All right, so progress update. We've now connected these two semantics to one another via polynomial time transformations. And next we'll look at the generating functions. Okay, so generating functions on their own are like a huge topic in mathematics, useful for counting things. But actually, it turns out that they're useful as a semantics for circuits as well, for tractable inference. And there's this sort of motivating result here for why this is an interesting question. So if you look at circuits which have certain structural properties called monotonicity and decomposability, doesn't matter what they are if you don't know this stuff. If you just look at distributions that can be efficiently captured by those kinds of circuits, computing the network polynomials, and this, by the way, is what some product networks do and what canonical probabilistic circuits do. And then you look at circuits computing generating polynomials, but making no structural assumptions about the circuits. There's a distribution there, the spanning tree distribution. So this can't be captured in the inner circle by anything of less than exponential size, whereas it's easily expressed in polynomial size by a generating function. Okay, so the actual question, is this because somehow generating functions are better for certain distributions, or is it in fact because you already know the punchline, because somehow those structural constraints that are typically used in practice are actually overly restrictive for some distributions? All right, so for our same toy example with two variables, here's the generating function. It also encodes the distribution in a supernatural way, where now to determine which, so every monomial still corresponds to a world. And to determine the monomial, you just take the values in that world and make them the powers of the indeterminates. So the constant term here is the all zeros world. The 0.4 x1 x2 monomial is the all ones world, and so forth. Okay, here the fact that you can already do marginal inference when you have a circuit representing this polynomial is like super cool. So, maybe non-obvious at all. Try to work it out. There's like a cool algorithm that lets you do this. But then its relation to the network polynomial isn't known, and so this is what we want to figure out. Again, there's one direction that's easy. So if you take the negative literals and just replace them with 1, you may have already noticed this, you get back to the generating function. And so now if we have a circuit computing a generating function, can we get back to the network polynomial semantics? Okay, and without going into details here, basically the same trick works. It turns out that there's a very similar expression with these sort of fractional gadgets and then this one bit at the top, which allows you to go from generating to network. And then here, this really cool Strawson result means that, notice those fractions now produce a division by 0 anytime one of the negative literals is 0. So this will happen on like all but one or something inference queries. And so actually you can't use this center like computation graph to do inference. You would have division by zeros all the time. So this Strawson result allows us to get back to the base sums and products language quite nicely. Okay, so the progress update here is that now we've connected network and generating semantics. And finally, we'll look at the Fourier polynomial. So again, this is sort of a ubiquitous subject in its own right, Fourier analysis. In fact, even the restriction to the Boolean case is very well studied. And here we're going to be looking at the Fourier transform of the probability mass function. And so this as well can be represented by a unique multilinear polynomial. And this semantics has been studied in the context of approximate inference in graphical models, and has also, again, been considered as a semantics for circuits called characteristic circuits. Okay, and here we don't even need the fancy division trick. Maybe if you know things about Fourier analysis, you might see this coming. I was very pleasantly surprised by this simple relationship. So generating polynomials in Fourier polynomials, they induce functions on all of Rn. But if you just look at their restrictions to -1, 1 to the n, and then 0, 1 to the n, respectively, they compute the same function up to a constant factor. Okay, so what does that mean? You can just sort of transform the leaves, transform the inputs to the other domain, and then the function, the circuit computes exactly what you want. So this is sort of the easiest transformation. Okay, so we've connected this back. So the punchline here is that, you know, if you have a circuit in any one semantics, you can efficiently get a circuit for the same distribution in any of the others, meaning that they're all tractable for marginal inference on the exact same class of distributions. And then I'll just quickly mention, because the Fourier transform is an involution up to a constant factor, if you sort of take the Fourier transform going from the likelihood to the Fourier semantics, and then you do it again, you'd get back to where you started, but you'd actually be stopping at different polynomials along the way. And so this is sort of, you know, the Fourier transform kind of naturally induces some new semantics here, which haven't been studied and might be useful in their own way. Okay, one last cool fact is that for non-binary random variables, it wasn't known previously whether you still have tractable inference for generating functions. So first of all, if you have a domain larger than just binary, 0, 1, you can sort of handle it for finite discrete domains by just using like a binary encoding. And so this is typically what's done, and this works. But it's interesting to wonder if there's sort of a way to treat categorical variables over larger domains as like more first class in the model. And generating functions give you a natural way to do this already. So generating functions, you know, they're not typically defined just for the binary case, they're well defined for discrete variables. And here the encoding is the same, it's just the values in the world are the powers of the indeterminates. Okay, but if you have a circuit computing this, can you still marginalize efficiently? This was the question we wanted to answer, and here, I guess, unfortunately, we show a negative result. So as soon as you have a domain of size 4 or larger, computing likelihoods even, not only marginal probabilities, but even getting a single probability of a single world is sharply hard in this setting. So, okay, so in conclusion, what we've done is we've shown, you know, several distinct circuit models are equally expressive efficient. We've sort of unified existing and introduced one new inference algorithms for them. We've shown inference is sharply hard in generating polynomials for circuits over domains of size 4 or more. Okay, and what are other interesting questions in this sort of research direction? A natural one is, how can this sort of theoretical progress be leveraged in practice? So maybe there are useful inductive biases in one semantics versus another. And then, are there more expressive efficient tractable representations in general? So this is a super interesting question, I think. We have sufficient conditions that capture a pretty rich class of distributions for which you can still marginalize efficiently, but maybe we can do better, and it's unknown. So for example, all the semantics we've had so far are multilinear. Is that necessary? We don't know. And that's it. Thank you very much.
Very nice, thank you. Questions for the speaker?
Thank you for the very clear presentation. So one thing I'm wondering is, if I take something like an Ising model, and I try to break down a representation, my understanding is that I could write a representation and then obtain, you know, marginals in a linear time. But then how expensive is it to construct the circuit? Do I not end up paying the price there instead of the marginalization?
Yeah, that very well may be true. So I'm sort of new to this research area in general. I don't even know that specific model and how you might write it down in this framework. I'd be happy to chat about it afterwards. Yeah, so there are definitely, yeah, so this doesn't say that like anytime you have a distribution now, you can express it in this language and get tractable inference. Certainly there are distributions which you can't. So yeah, but I'd be happy to discuss like the specific one you're asking about.
Yeah, sounds good.
Yeah.
Okay.
Very nice talk. And I have a quick question. So you talked about these different semantics, and I was wondering, so now they are all equivalent, but there are any benefits that you can envision in terms of, I don't know, learning the circuit or something?
Yeah. Very good question. Yeah, so very good question. So I don't have a perfect answer yet, but sort of guessing. It might be nice, say, to incorporate negative weights in these circuits by using one representation space versus another. This is just the first thing that comes to mind, because it's well known that negative weights in these circuits makes the model more expressive, but typically in practice, say in some product networks, in order to get a valid output, knowing that the polynomial you're representing is of the correct form, having all positive probabilities or non-negative probabilities, we sort of have naive sufficient conditions. And so whether using one semantics versus another to maybe get a more interesting class of distributions where we can incorporate negative parameters using sufficient conditions in a different class, that may be an interesting direction for future work.
Any other questions? Yes.
Thank you. Very, very nice question. I just wonder about the continuous variable. Is there any way to bridge this?
Yeah, great question. So I had the poster session yesterday and everybody asked this question. So maybe I should have said something. Yeah, so I mean, maybe in defense of the binary case, after being trained in computer science, you see Boolean functions everywhere. Certainly the computers are all working with bit strings in the end. So in some sense, I view this as like a very natural core of this problem that we still don't fully understand. But then it's also a great question if there's like nice formalisms for the continuous case where we can ask similar questions. And there are sort of continuous analogs to a lot of these semantics, which I don't understand well right now, but might be super interesting to study in terms of their comparisons and expressivity.
All right. This was a very nice session. Let's thank all the speakers once more. And thanks very much for attending.